Hello, everybody. I'm Fedor, and I'm presenting a joint work with Itai, Arieli, and Yakov Babichenko from Technion, and Omer Tamuz from Caltech. In this work, we consider a very basic setting of Bayesian communication. So there is a binary random state theta, and the prior probability of theta equals 1 is p. There is also a group of n receivers. They don't observe the state, but they get private signals about theta. So the first receiver gets a signal as 1, the second receiver gets signal as 2, and so on. And of course, there is a joint distribution over collections of signals, and this distribution depends on the realized state. Receivers know this distribution, so they can perform Bayesian updating, and the first receiver gets a posterior P1 prime, which is just the conditional probability of a high state given her signal as 1. The second receiver gets posterior P2 prime, and so on. So we get a vector of posteriors, and it's a random vector since it depends on a random state and also on randomness in signals. So each signaling policy induces a distribution over such vectors, a distribution over the n-dimensional unit cube. And the question we ask is, what are the feasible distributions on the unit cube? In other words, what are the distributions that we can induce by some signaling policy, where we can select the sets of signals for each of the receivers and also the joint distribution of signals for both states. Why is it interesting? First of all, one can imagine a more general dynamic learning setting where receivers get some information, maybe they exchange some messages, get some other pieces of information, and so on. But such a dynamic learning process can be reduced to the static setting that I just described if we consider the trajectory of the learning process as just one signal. So our question is equivalent to asking what are the possible outcomes of learning processes. We can also look at this question from decision theoretic point of view. Imagine we are observing distribution of beliefs over the population, and we can ask whether it is compatible with Bayesian rationality, whether it's compatible with existence of a common learning process. And again, it's the same question about feasibility. And of course, the question of feasibility also highlights the limitations that the information designer has in inducing certain beliefs among the receivers. And we will discuss it in more details at the end of the talk. So what is known about feasibility? The case of one receiver is completely understood. So it's known that the average posterior must be equal to prior. This is the so-called Martingale property. So on average, beliefs do not change, and it can be seen as a rationality property, namely time consistency of beliefs. And there is a celebrated result, the splitting lemma, that is usually attributed to Aumann and Maschler, but it was also known to David Blackwell even before. And this lemma states that the distribution on 0, 1, the distribution of posteriors for one receiver, is feasible if and only if it satisfies the Martingale property. It's necessary and sufficient condition. Beyond one receiver case, the understanding is quite sparse. There is a recent paper of Ziegler where he derives a certain additionally necessary condition on feasibility. And also there is a paper of Matevet, Perega, and Taneva where they consider a related question of feasibility of belief hierarchies In contrast, we are interested in feasibility of first-order beliefs, and we are looking for an answer in terms of first-order beliefs, and we want a characterization of feasibility, so an analog of splitting lemma, and such analog was not known. And this is what I'm going to describe to you now. So let's focus on the case of two receivers. And it's clear that the martingale conditions should be satisfied for both of them. So it's clearly a necessary condition for feasibility. However, it's not sufficient, as we see at the following example. So let's look at a distribution that places equal weight on the two anti-diagonal points. This distribution satisfies the martingale condition for prior 1/2. However, I claim that it's not feasible. Let's look at the situation when the posterior of the first receiver is 1/4. Then she knows that the posterior of the second receiver is 3/4. And vice versa. The second receiver knows the posterior of the first. And actually, you're going to reconstruct the whole belief hierarchy. The first receiver knows that, the second receiver knows, and so on. And there is a celebrated result of Robert Aumann, the agreement theorem, which says that if posteriors are common knowledge, as in this case, they must be equal. But for this particular distribution, they are unequal, so this distribution is infeasible. Of course, intuitively, if posteriors are almost common knowledge, they must also be close. And we confirm this intuition by proving a new quantitative version of agreement theorem. So let us pick a subset A of posteriors of receiver 1, subset B of posteriors of receiver 2, and let's look at the quantity delta, which is just the difference between the average posterior of the first receiver over the set A and the average posterior of the second over the set B. And then the following pair of inequalities holds, where the left-hand side is just the measure of the red region, and the right-hand side is the measure of green region. And this bound holds for any feasible distribution mu, and it shows to which extent receivers can disagree. This bound must hold for any subsets A and B. To get more intuition about this bound, let's look at a particular case when red measure and green measure are both 0. In this case, if the first receiver has her posterior in set A, then she knows that the posterior of the second belongs to the set B, and vice versa. The second receiver, if her posterior is in B, she knows that the posterior of the first is in A. And again, you can reconstruct the whole belief hierarchy and see that the event that the pair of posteriors belongs to the yellow region is common knowledge. And so by Aumann's agreement theorem, the average posterior of one receiver must be equal to the average posterior of the other. And this is exactly what our bound gives in this case. And of course, it holds also for the situation when the red measure and green measure are not 0. And in this case, it provides some restrictions on how much our receivers can disagree. So this bound gives an additional necessary condition for feasibility. And our main result states that the pair of conditions, the martingale property and this bound on disagreement, are necessary and sufficient for feasibility in case of two receivers. So feasibility is determined by two rationality properties, time consistency and agreement. In the paper, we also offer a no-trade interpretation of this theorem, namely, a distribution is feasible if and only if you cannot construct a certain money pump extracting money from receivers. The result extends to more than two receivers, but it loses the agreement interpretation, but keeps the no-trade one. The proof is hard in the direction of showing that the two properties imply feasibility, and we do it by reducing the question to existence of some dominated measures with given marginals, and there is a rich mathematical literature on this subject, and we rely on the papers of Kellerer and Hansel and Trolley. Let's look at some applications. And for simplicity, let's assume that the prior is 1/2 and there are just two receivers. Let's ask the following question. Can posteriors of the two receivers be independent? It means that the information that the first receiver has tells her nothing about the posterior of the second receiver and vice versa. Intuitively, this must be impossible, since if my posterior is high, it means that it's likely that the state is 1, and if the state is 1, it's likely that posterior of others is also high. However, let's just ask even a more ambitious question. Is the uniform distribution on the unit square feasible? And the answer is yes, and this is just a simple computation checking that the distribution satisfies the disagreement bound. We also show the characterization of feasibility for product distributions. So let's pick a measure phi on 0, 1, which is symmetric with respect to 1/2. And we show that phi times phi, the product distribution, is feasible if and only if 5 second order stochastically dominates the uniform distribution. In other words, the uniform distribution is the most informative among feasible product distributions. One can also ask a similar question for 3 receivers. Is the uniform distribution on the unit cube feasible? And surprisingly, the answer is no. And there are some other surprising observations in the paper. Now let's briefly discuss Bayesian persuasion. So now we have a sender who observes the realization of the state and who is going to decide on the information policy, on the signaling policy. And he has a utility function u on pairs of induced posteriors. So again, we focus on just 2 receivers and prior 1/2. And the goal of the sender is to maximize his expected utility over all signaling policies, or equivalently over all feasible distributions. Of course, usually it is assumed that receivers also have a certain utility function and they take some actions upon receiving their signals. And this setting is equivalent to ours if we assume that the utility of a receiver depends only on her action and the state, but not on actions of other receivers. So our sender faces actually an optimization problem, which is a maximization of a linear functional over a convex set of feasible distributions. So it's easy to check that it's convex. So the optimal policy is always attained at an extreme point of this set. And we show that there are extreme points with countable support, which means that optimal persuasion may require an infinite number of signals, and it is in a strong contrast with one receiver case where 2 signals are always enough. let's briefly look at a couple of examples. In the first one, the sender wants to maximize the disagreement between the beliefs of the two receivers. This is his utility function. And for alpha from 0 to 2, the optimal policy is simple, just revealing the state one of the receivers and tell nothing to another. However, for large alpha, the uniform distribution on the unit square does a better job. However, we don't know what is the exact optimal policy in this case. A more interesting example is the case of sender that wants to minimize the covariance between the two posteriors. Intuitively, posteriors cannot be anti-correlated. Again, our receivers make guesses about the same state. However, this intuition is wrong, and the optimal value is -1/32, and it is achieved at the following optimal policy. Okay, so it's time to summarize. We saw that the case of one receiver and several receivers are significantly different. In particular, you have some new obstacles for feasibility that arise from the quantitative bound on disagreement. And also, for optimal persuasion, you may need an infinite number of signals. There are also many open problems around our results, and I will mention just one of them. Do we actually need a continuum of signals for optimal persuasion? In other words, are there non-atomic extreme points of the set of feasible distributions? That's it. Thank you.